A-level physics lesson 48, terminal speed. Yes, this lesson in GCSE is often called terminal velocity, and I've always had a problem with that term velocity in that title. It should be terminal speed, that's what I teach. Anyway, terminal speed. It is not the highest speed that a body can reach, which is, again, a very common misconception. No, this is the speed of a body when in equilibrium. Don't know how many L's are in equilibrium. It's the speed of a body when in equilibrium, when the resultant force is equal to 0. That's it. Lesson ends. Well, not quite. We need to go into a little bit more detail than that. There is no maximum speed an object can take. Now, the classic example that is given is the idea of a skydiver jumping out of an aeroplane. And the skydiver who's falling towards the ground, their speed will increase up to some amount, where it doesn't appear to increase anymore. Then they open a parachute and their speed decreases down to some amount. And the amount the speed increased to when the parachute wasn't opened, this is before the parachute was opened, that speed is the terminal speed in that situation. When the parachute then opens and the speed reduces, it reduces to the new terminal speed. So let's have a look at that example in some more detail. So skydiver example. And let's put a little underline there because it's a little subtitle or something. Right, skydiver example. So we've got, let's draw a graph. And I'm going to draw a graph of velocity versus, I'm going to do speed. Speed versus time. I'm going to give myself plenty of space to annotate what's going on in this particular graph. So this is going to be speed. There it is, speed, and this is going to be time. Now, when the skydiver first jumps out of the aeroplane, their speed is going to be 0, and then it's going to be increasing. Now, let's draw a line like this, and I'm going to say that this line has a gradient of this line is going to be equal to 9.81 meters per second squared, like that. That's going to help me with this. So the skydiver jumps out and their speed is going to start increasing. Oops, let's do a better job. Is going to start increasing at the rate of that grey line. And do the best I can because I want it to have the same gradient initially. There we are, that's better. And then it goes up to some sort of maximum, like that. So we've got different stages here. We've got stage 1 all the way down here. And this is where the velocity is equal to 0. In that case, the resultant force is equal to the weight, just like that, and therefore the acceleration is equal to g. Fine, okay. The air resistance in that is 0. There's no air resistance. That's important. So air resistance, I'm going to call that D for drag. I'm going to put that as air resistance is equal to 0. Which is why the resultant force is just equal to mg. And that's in this first stage here. Then what happens? Well, then we get this stage here. Now, in this stage, D is increasing. D is increasing. And why is that? Because D depends on v. It depends on the speed that we're moving through the air. Faster the skydiver moves through the air, the more air they move out of the way per second. That is going to increase that drag. So because d is increasing, F is going to be equal to mg subtract d is decreasing. Therefore, the acceleration is decreasing. Now, do not be mistaken here. The speed is still increasing. Even though there's air resistance, the air resistance does not cause a reduction in speed. It causes a reduction in acceleration. But the body is still getting faster. Okay, this is how it works. Until we get to here. Now, here we have air resistance equal to the weight of the body. Now, the acceleration is now equal to 0. The acceleration is decreased to that point that is 0. Therefore, the resultant force is equal to 0. And because the resultant force is equal to mg minus d, that means that mg must equal, in magnitude, d. So we have reached our terminal speed. The air resistance is equal to the weight. Our speed is at a maximum. But then let us suppose that we now open parachute. How do you spell parachute? Parachute, something like that. We open our parachute at that instant in time. What are we going to see happen? We're going to see a reduction in speed down to some constant speed down there, like that. So what's happening in this section here? Well, now the acceleration is less than 0. It's negative. What does that mean? That means that the drag is going to be greater than the weight. It's greater than mg. Why can't I not do a greater than symbol? There we are. So the resultant force is up. So F is up. The resultant force is up. And we use the same equation from down here. F equals mg minus d. But d is bigger than mg, then F is negative. So the acceleration is negative, as it should be. And so because the speed is positive, but the acceleration is negative, it causes a slowing down. And that's what's happening there. So we're slowing down with the parachute open because our drag force becomes bigger than our weight. But as we slow down, that causes a decrease in the drag. So by the time we get down to here, slowing decreases d. So down here, people often get surprised by this. The acceleration is equal to 0, therefore the resultant force is equal to 0, and therefore the weight is equal to the drag force. The drag force, when we open the parachute, at that given speed was higher than the weight, which is why we slowed down. But we only slowed down to the point where the drag force became equal to the weight again. And then once the drag force is equal to the weight again, we've reached our new terminal speed. And then, of course, we hit the ground. So that's the classic skydiver example, breaking it down to all those sections. I can't tell you how many students I've had who, despite being taught this, when you ask them, where's there a bigger air resistance, here or here, Some of them will say, oh, well, I went back by accident. Let's go back into the notes. Some of them will say the air resistance is bigger at the, let's just delete them. Some people will say the air resistance is bigger at the top because that is where we're traveling faster. So that must be a bigger air resistance because we're traveling faster. Some people say the air resistance is bigger here because that's the reason we're going slower. And the parachute's open, so that means there's more air resistance. But the fact is the air resistance is the same in both those places, and it's equal to the weight. Don't fall foul of that common misconception. So that's the skydiver example. Actually, it's not just for falling that we have to consider terminal speed. And so in the classroom, what I do is I get a driving simulator out. We measure the terminal speed of a car. So we could say a driving car example. Now, when we drive a car, the force from, let's say, force from the engine, to keep it simple, is going to be in the forward direction. So let's draw a very simple car. This looks more like a van, but that's fine. I can drive a van. There we go. We have our force in the forward direction, which is our driving force. And the nature of that will become clear later. And let's just label that driving force. And then we've got our drag, or our air resistance. And if our driving force stays constant, then the air resistance increases as the speed increases. And this is no different resistance. This is no different to the previous example at all. It's exactly the same. If you plotted a graph of the speed of the car, or in this case the truck, versus time, so speed versus time, it would do exactly the same thing. We'd have an initial acceleration due to the driving force acting on the car and no air resistance. And so we could calculate what the acceleration would be by doing F divided by m. And then we end up with 0 acceleration at the end. But as it gets faster, as the air resistance increases, that doesn't cause it to slow down, it just causes a reduction in the acceleration. The acceleration is the gradient. Well, it's the magnitude of acceleration is the gradient of this particular graph. So at any given point, at any given moment in time, the acceleration is going to be equal to the driving force minus the air resistance. Should I call it driving force? Let's call the driving force Fe for engine, and let's call the air resistance Fd for drag. So the force from the engine, subtract the force from the drag divided by the mass of the vehicle. That's true at any given moment. So what's the relationship between the air resistance and the speed? Well, that's complicated. So air resistance versus speed. Well, yeah, and that's complicated because there isn't one single way of calculating air resistance. If you've got a spherical body that's moving slowly enough through the air, then the air is going to move, or any fluid, then the air, or whatever the fluid is going to move around it. And you're going to get laminar flow of that fluid around the object as the object moves through the fluid. That's very different if the object is going fast enough, or if it's an odd shape, and it causes chaotic turbulence of the fluid as it strikes it. So if the object is spherical and slowly moving, then we could say that the drag force is actually equal to 6 pi eta RV. This is Stokes' law. There's a lot of parts to this equation. So eta is the viscosity of the fluid, maybe air, maybe water, it doesn't matter. R is the radius of spherical object, or spherical body. And then V is the speed of the body relative to that fluid. And when you've got a spherical object is small enough that its terminal velocity is quite low, then it can reach terminal velocity, and the weight of that object is equal to Fd, and you can equate it to Stokes' law. And that becomes useful later on. But what if there is air resistance? Well, we can do a bit of dimensional analysis here to work out. This is a little clever thing we can do. We can say, what do we think the drag force is equal to? Well, I think the drag force is going to be dependent upon the density. I think it's going of the fluid. I think it's going to be dependent on the speed that we move through the fluid. I think it's going to be dependent on the cross-sectional area of the object as it moves through the fluid. So I've used square brackets to indicate we're interested in dimensions here. So what we could say is we think it's related to those dimensions, but we don't know what these powers have to be. So what did I say the next one was? Did I say it was V and then A? So with dimensional analysis, what we're saying is, because there's an equal sign in the middle, we're saying that the dimensions of this force must be the same as what's on the right-hand side, which means how many powers of rho do we need? That's the density of the fluid. How many powers of V do we need? That's the speed we move through the fluid. And how many powers of A do we need? That's the cross-sectional area of the object. Well, we could figure this out. So what we're going to do is we are going to write what those dimensions are in base dimensions. So rather than force, this is a mass multiplied by the square of a length multiplied by 1 over the square of a time. Now, how did I get the dimensions of force? Well, I know that F equals ma. M is a mass, it has dimensions of mass, and A is an acceleration, which has dimensions of length. I've made a mistake there, that's why you always check things, of length multiplied by time to the -2. So it's similar to units, and you can actually do something which is basically dimensional analysis by just looking at units and making sure the units balance on either side of the equal sign. But just as we've got 7 SI units, they are the units for the 7 base dimensions. Meters is an SI unit. That's the unit for lengths. Areas, well, that's going to be a length times a length. So it has dimensions of length squared. Volumes is length times length times length. It has dimensions of length cubed. Speeds are length divided by time, so length times the -1. Accelerations are length divided by times again. So densities are masses and then divided by volumes, like that, but we don't know what the power A is. V is a speed, which is lengths divided by times, and then A is an area, which are cubes of lengths. And then we just have to figure out what A, B, and C are. Well, you can see that there's only one M on this side, and there's only one M there, so A has to equal 1 to make them balance. So we can say A equals 1, and then we can write this out again. We can now write this out again and say that's equal to ml to the -3, should be a minus, and then lt to the -1. We'll work out what B is in a second. L to the 3, we'll work out what C is in a second. Oh, I forgot to write the B down. B and L3. C. So on the left-hand side, we've got 10 t to the minus 2. On the right-hand side, t only appears once, and it's t to the minus 1. So the only way to make that work is to say that b must equal 2. Now, if b equals 2, this becomes ml to the minus 3 multiplied by l squared t to the minus 2. Now, I'm writing it like that because I'm going to do some cancelling in a second. L to the minus 3 and L to the 2 cancels, and that leaves me with L to the minus 1. Is that right? Yes, it will be. And we've still got a t to the minus 2 here. And then we've got L to the 3c. Now, that has to balance with what's on the left-hand side there. So we can go through the list and we can check. We've got m to the 1, m to the 1. We're good. We've got t to the minus 2, t to the minus 2. We're good. But then we need L to the 1. We've got L to the 3 and L to the minus 1. So if c equaled 1, that would balance. And that's how you do dimensional analysis, just like that. So c equals 1, then we end up with ml t to the minus 2, which is exactly what we need. So using all these, we end up with f is proportional to, and it's rho to the power of 1, it's v to the power of 2, because b is 2, and it's a to the power of 1. And so you can see that f is proportional to v squared if a and rho are constants. So Stokes' law, f is proportional to v, but if we've got turbulent flow of the fluid around the object, f is proportional to v squared. So I'll leave that there. It was a nice opportunity to show you some dimensional analysis. I went through it quite quickly, but I do cover dimensional analysis in the video of the transition from GCSE to A-level physics, which is part of that transition series. And if I remember, I'll put a link somewhere. It should appear on the video somewhere or in the description, so you know how to find that. Right, I hope you found that useful.